Welcome back, everyone. What we're going to look at now is we're going to look at how to use our CAS to do this anti-differentiation work. So what I want to start with, though, is obviously an equation. So we're going to say f of x, f dash x, because we want to start with the derivative because we're trying to go backwards. F dash x is equal to, and I'm just going to plot numbers in here. It's going to be 2x squared plus 6x minus 9. And one of the things I know is that f of 2 equals 0. That's just one of the things I know. So, with that information, we can use our CAS. So what you're going to do is you're going to hit keyboard. You're going to bring up the keyboard. You're going to look at Math 2. And then you're going to go down to the third row, fourth column. And you're going to see a symbol that looks like this. And it looks like that. All right, this is your integral symbol. So third row, fourth column. And it brings up all this extra stuff here. So in these top two boxes, so this box here and this box here, leave them alone. All right, at this stage, at unit 1 and 2, you do not need to use those two boxes. Leave them blank. What you will do, though, is you will type in your equation, and then in the box at the end where it says D, you're going to put in the pronumeral that you have been using this whole time. And when we hit enter, we get given this. Now, if you were watching the last episode, or the last lesson, what's missing from the end of that? A constant. Yes, very good. All right. Your CAS will not put the constant in for you. You need to do that yourself. All right. You need to make sure that if you're using your CAS to do this, you do not forget your constant. So, what I am going to do, though, is, because I want to try and solve it, I'm going to define f of x is equal to that, and then I'm going to put the c in myself. So now whenever I do f of x, I get that with the constant. Well, if I know that f of 2, if I know that f of 2 equals 0, then I get that. All right, so I put 2 into that equation, and it gave me that, and I know that it's equal to 0. So I have this little equation here. And now, if I drag that down, out the front, if I go to Math 1, solve, comma C, and it's equal to 2/3. And so I can now go back and I can I can say with confidence that f of x is 2x cubed over 3 plus 3x squared minus 9x plus 2 over 3. All right. So I've now used my CAS. I've done the anti-differentiation. I have got the original equation with a constant. I've used the other pieces of information to solve for that constant. And then I have stated the whole equation. So let's do another one. And this time what I'm going to do is I'm going to use my CAS to define things so that I can manipulate them later. So what you can do with your CAS is you can define, so say we have f of x. Now, our CAS, unfortunately, does not recognize f dash x. It doesn't know what that is. So if I went in here and I typed f dash x, it just doesn't know what to do with it. All right. But what I can do is I can say f of x can be my derivative. So let's set up an equation. Let's set up an equation here. For my CAS, I'm going to start with the fact that f dash x is equal to 5x squared plus 18x minus 12. So that is my derivative equation. I have a piece of information that f of 3 is equal to 0. All right, so I'm actually given an intercept. What I can do is I can define on my CAS, define f of x as being I can do this. I can define. So what I'm going to do is on CAS, f dash x has gone to f of x. It's just a function that I'm just naming it for my CAS. And f of x is going to be, so paper, CAS. So on paper, it would be f dash x and f of x. On my CAS, I'm going to say that f of x is the derivative and g of x is the antiderivative. So what I'm going to do is I'm now going to define g of x as being the derivative of f of x with respect to x plus c. So I'm going to say that g of x is equal to the integral or the antiderivative of f of x with respect to x plus c. So now when I type, hang on. So you have to make sure that plus c, when you type it, you have to make sure that you are outside of the integral in the CAS. But what it does now is it takes the antiderivative of the original function and it whacks the constant on for you. All right. Then And then we can go solve C is minus 90. And then we can write out the whole equation using all the information that we've got. But what's cool is once you've got this set up in your CAS, if I go back and I change this original f of x equation, everything cascades down. So I can go back and all of my changes cascade down. And then I can go in here and I can type in the piece of information that I know. And it will fill in the blanks for me. So it will go back and it will make sure that everything I've got makes sense. All right. So you only need to set it up once in your CAS, and then you can manipulate everything. As long as you get it in your head, the way the CAS works and the way it actually works on paper. So let's have a look at some of the questions that you did last period by hand, I hope, and see how they work with the CAS, especially some of these more complicated ones. Because normally, to integrate some of these, you would need to expand them. However, CAS don't care. CAS can work with it. So what I've got here from question 1 of 17E. So let's see what they look like when we do them on our CAS. So again, integral symbol, x bracket x plus 1 on x dx. And here you'll see that the CAS doesn't quite know what to do with it. What are you going to have to do with that first before you can do anything with it? All right. So instead of doing it as 1 on x, let's do it like that and see if that does anything. Nope. But what we have to remember is that x can't be 0 as well. We can expand. Expanding is fine. In fact, that is probably what you're going to have to do. And what you'll see is if you try and do some of these other ones, so dz squared, z dz squared, z minus 1, with respect to x? No, with respect to z. It will do some of them. It will do some sometimes for you. But what do you notice about what it's probably done first? All right, it has expanded them first before doing anything else. It has expanded them. Let's try another one. 2t minus 3 squared with respect to t. And it's produced that. Remember, A and S just simply takes the last answer that it's done and do the operation to it. So we could take what we've done here and expand that first. Then anti-differentiate it and we'll get what we've got here. It's all cancelled down, by the way. And the last one, t minus 1 cubed. So, if the derivative of an equation is always 1 power lower than the original, then the antiderivative is therefore going to be 1 power higher. So that way you can always sanity check your answers. If the original function that you're working with was t minus 1 to the power of 3, then whatever answer you get is going to be to the power of 4. So, what I would like us to do for the remainder of the period is to look at some of the end questions of 17E. So we're talking 9, 10, 11, 12, and 13. So, what we're going to do is we're going to work through two together. I would like people to make suggestions in the chat so that we can work through this as a class. The CAS is necessary for this, so I'm just going to shrink it a little bit. And we're going to pull apart the question. We're going to look at the question, and we're going to try and pull it apart. So, find the equation of the curve f of x. All right, so we need to find the original function, which passes through the point 2 minus 6. And for which f dash x, so the derivative, is this. So we're given two pieces of information that f dash x is equal to x squared x minus 3. And we're also told that f of 2 is equal to minus 6. So I've taken that there and converted it to function notation. and I've got this and established that as what my derivative function is, and I'm going to anti-differentiate. So before I can do anything to this, I should probably expand that. So that's going to be x cubed minus 3x squared. All right, so we're going to anti-differentiate that. So anti-differentiation of this is going to be add to the power, divide by the new power. Add 1 to the power, divide by the new power. And then there's no constant on the end, so there's no lower powers, but I'm going to add that plus c on. So my current answer for f of x is that. Now is when we take a look at the other piece of information that we have, and we're going to use that to find c. So I know that when x equals 2, y equals minus 6. So that's going to be 2 to the power of 4 divided by 4 minus 3 times 2 to the power of 3 divided by 3 plus c. So that those 3's will cancel out already. I should have done that earlier. 2 to the power of 3 is 8. So I have minus 6 equals 2 to the power of 4 is 16 divided by 4 is 4 plus c. So 4 minus 8 is minus 4. So minus 6 equals minus 4 plus c. Add 4 to both sides, minus 2 equals c. So I now have a full equation. X to the 4 of 4 minus x cubed minus 2. So that is the full answer for that question. So let's take a gander at question 10. The curve f of x has a derivative 4x plus k, where k is a constant and has a turning point at minus 2, minus 1. All right, so that is all the information we're given, and we're expected to calculate the value of k. So first things first, we have this curious piece of information. What's the turning point got to do with anything? So we have a turning point. Turning point is the derivative is 0. Yeah. So what they're saying is that f dash minus 2 is equal to 0. So that is automatically a thing you can do. If you say turning point at minus 2, minus 1, then you can automatically go, well, okay, fine, f dash minus 2 is 0. So now I can go in here and I can go, well, if I replace the x with minus 2, f dash minus 2 is equal to 4 times minus 2 plus k. I know that f dash 2 is equal to 0, so I can go 0 equals 4 times minus 2 plus k. 0 equals minus 8 plus k. K is therefore equal to 8. Find the coordinate of the point at which the curve, so the curve is this, as stated before, f of x. So that's the original function. Find the coordinates of the point at which the curve meets the y-axis. So that means, what is the y? So meets the y-axis. Fancy falutin way of saying y-intercept. So when the curve meets the y-axis, that means we're looking for the y-intercept. So first things first, we have f dash x, which is equal to 4x plus 8, because we just worked that out. If I anti-differentiate it, I'm going to get f of x equals 2x squared plus 8x plus c. Do I know anything else about the original function? Do I know anything about f of x? Yeah. All right. So even though this is a turning point at f of minus 2 minus 1, the fact is that this is also, it is also a point on f of x. So f of minus 2 is equal to minus 1. That's going to be 2 minus 2 squared plus 8 times minus 2 plus c. And then we can solve from there. Because remember that when x equals 0, then that's going to be the y-intercept on the end there. So we need to find what that c is going to be. So minus 1 equals, so minus 2 squared is positive 4, so that's equal to 8. 8 times minus 2 is minus 16, plus c. Minus 1 equals minus 8, plus c. C is equal to 7. So when x equals 0, y equals 7. So the full equation, if it was being asked, would be f of x is equal to 2x squared plus 8x plus 7, because indeed when x equals 0, y does indeed equal 7. So that comes down there, and that's where that comes from. So add 1 to the power, divide by the new power. Put a constant on the end of it. Look for any other information that you can work with about your original function, and then use that to put and to find the value find the final value for your constant.